All right, everybody. What we're focusing on today in section 6.4 is basically how do we simplify any radical? Okay, so how do we do square roots, cubic roots, fourth roots? I'll walk you guys through this. I'll also be showing you, again, how to use a calculator and showing you some quick tips for that. But we have to know our vocab first of all. So up at the top, it's got all these boxes pointing to various things. So again, know your vocab. That little n in front on the far left side. So again, you might see a different number there. You might see like a 3 or a 4, just making it a cubic root or fourth root. That's what's called the index, that little number in front. The next one, the top right, the box, what it's pointing to is just simply the radical sign. So it's just the radical sign, radical symbol. And then underneath, what you're taking the square root or the cubic root of, whatever that number is or that expression, what that is going to be, it's called the radicand. So knowing your vocab will be useful. Okay, so come back to this, glance back at it if you need to. The principal root, when you're talking about just the principal root, it's really just talking about the positive root. So principal is positive. So as an example, if you just see the square root of 25, if I just ask you for the square root of 25, this just indicates that I'm looking for the principal square root of 25. I just want the positive square root of 25, which would just be positive 5. However, if you see negative out front, if I ask you for the negative square root of 25, well then that's going to be negative 5 because it's saying I want the opposite of the principal square root of 25. And then if you see a plus and minus out front, the plus and minus square root of 25, then I'm asking for both answers, positive 5 and negative 5. Okay? Um, in this box, I'll come back up here and talk about this too in a second. But technically speaking, if you have, so we have all these different case scenarios, but if you have an odd index, right? So if you have an odd number out front as your index, technically you're only going to get one real root. So let me show you an example. If I asked you for the cubic root of 8, okay, so again, I have an odd index, 3 is my index. It is an odd number, 3 is an odd number. If I asked you for the cubic root of 8, I'm basically asking you what number times itself 3 times is going to be 8. So you can kind of sit here and guess and check if you'd like to. But how you actually type this into your calculator if you're using the TI-30. So you want that little 3 in front, right, for your index. Again, we know where the square root's at. I'm not asking you for the square root of 8. I'm asking for the cubic root of 8. So here's how you get that little 3 in front. You actually want to hit the 3 first, and then right above the square root symbol in your calculator is a little green button. You see that little X in front of the square root? Again, right above the actual square root button. So if I go to second and I hit the one with the little X, you see the 3 actually shrink down to be the index. So I'm taking the cubic root of 8 and it tells me that it's 2. And again, the reason being is because 2 times 2 times 2 is going to be 8. Okay, so when you're taking a square root, the question is, well, what number times itself is going to be that number as your radicand? But this time, since the cubic root, what number times itself 3 times is going to be your radicand, and that again would just be 2. But like we said, if you have an odd index, you're only going to have one real root. That root's going to be positive 2. Okay? Versus if you have an even index and a positive radicand, technically speaking, you do get 2 real roots. So let me kind of explain this. So if I asked you for the square root of 9, technically you do get positive 3 and negative 3. Okay, so again, this has an even index. So when you have a square root, technically speaking, there is an invisible 2 here as your index. We just don't write it. Okay, so just like, if I write just x by itself, secretly we know that's x to the first power. We just don't write the exponent. Same idea for this one too. Okay, so square roots, that's an even index. But again, when you take the square root of 9, you technically do get 2 real roots because if you multiply 3 times 3, that gives me positive 9. But if I also multiply negative 3 times negative 3, I also get positive 9. So technically, like I said, you do get 2 real roots. However, you still want to pay attention to this. Okay, so we just talked about previously. If I'm asking you just for the square root of 9, technically I'm really just asking you for the principal square root. So I'm really just looking for the positive number, but you do actually have 2 real roots, if that makes sense. Okay, for the next one though, if you have an even index, but now you have a negative radicand. Okay, so underneath is going to be a negative value. So let's say I'm taking the square root of, I'll just do -9. Okay, so negative number underneath. You're not going to have any real roots. There's 0 real roots, but there's 2 imaginary roots. Again, technically speaking. You'd have positive 3i and also negative 3i. And again, for the same reason as right above. So if I multiplied 3i times 3i, that would be -9, but so is negative 3i times negative 3i. Okay, but like I said, up above, if I'm asking for just the square root of -9, technically I'm only asking for the principal square root. Okay, the last one, if you have a radicand of 0, it's always going to be 0. So it doesn't even matter what the index is. If the radicand is going to be 0, there's only going to be one root, and the answer is going to be 0. So square root of 0, it's obviously 0. Cubic root of 0, it's going to be 0. Fourth root of 0. So like I said, it doesn't matter what the index is. Okay, if the radicand is 0, the answer, the root, is always going to be 0, no matter what. All right, so let's go through some examples down below here. So for the first one, we're looking for the positive and negative root, right? The plus and minus, positive root and the negative root. So my answer is going to be plus and minus. However, when we're taking the square root, if you have a monomial like we have here, 16x to the 8th, you're taking the square root of each individual term. So I kind of break it up into little mini problems like this. Okay, so take the square root of each term by itself. Answer is going to be plus and minus. Square root of 16 we know is 4. The square root of x to the 8th. Here's what you're doing for this. Okay, think about what x to the 8th is. It's x times itself 8 times. Okay, there's x times itself 8 times. I'm basically asking how many groups of 2, since it is a square root, how many groups of 2 can I pull out from 8x's? How many groups of 2? Well, this would be 1, 2, 3, 4 groups of 2. So fully simplified, the square root of x to the 8th power is just simply x to the 4th. So fully simplified, we'd have positive negative 4 x to the 4th power. Okay, and same idea for the next one. So moving on to cubic roots. So we're going to take the cubic root of each term. I'm just going to kind of break it up to little mini problems. We're going to take the cubic root of each and every single number, or each and every single variable as well. So for the first one, cubic root of 8, we know is 2. So 2 goes out front. The cubic root of x cubed. Now what you're asking yourself, since it is a cubic root, right, is how many groups of 3, since it's cubed, how many groups of 3x's can I pull out? Well, I could pull out one group of 3. So that's just going to be an x. Okay, so x the first power because that's one group of 3. And then same thing with the y. How many groups of 3 can I pull out of 6y's? Well, that would be 2 groups of 3. Okay, and again, if you need to expand it out, you have 1, 2, 3, 4, 5, 6. But like I said, there's 1 and there's 2 groups of 3. So it'd be 2x y squared for your final answer. Okay? For the next one, we have negative square root of the expression q cubed plus 5 all being squared. Well, I want to mention to you, if you're taking the square root of a quantity that's already squared, right? So I'm focusing right now on this. This is the first thing that's popping out to me. I'm taking the square root of something squared. Those are inverse operations of each other. They basically cancel each other out. So my answer, negative out front, my answer would just be negative. Again, these just cancel each other. All I have left is the expression underneath. And this would be my final solution. Okay, we'll see more examples like that too on the next page, even down below as well. So I'll kind of explain that a little bit better. But the last one, number 4, taking the square root of negative 4, answer is just 2i. So again, when it's just a square root by itself, I'm just asking you for the principal root, just the positive. Okay, so answer is just positive 2i. In the next row, okay, so we're taking the positive and negative square root of 36x to the 12th. So again, if you need to kind of split it up, you're taking the square root of each term, but this would just be positive negative 6, and x would be to the 6th power, because you could pull out 6 groups of 2x's. Okay, and you could always just think about it too. I'm really just doing 12 divided by 2. Again, just dividing it by my index. 12 divided by 2 would be 6. Okay, so these are coming out nice and pretty for us, not too complicated. The next one, we're taking the 5th root, oh boy, of 243, 5th root of a to the 10th, and the 5th root of b to the 15th. Okay, if you don't know what this is off the top of your head, you might need your calculator a little bit. So we want the fifth root of 243, right? So again, you gotta hit the 5 first. Now shrink it down. So you want the little X in front of the radical. You want that button. So again, second, and then the one that's highlighted right now. 243, I type it in, it tells me that it's 3. Because 3 times 3 times 3 times 3 times 3, I need one more, is 243. Okay, so 3 times itself 5 times. So this would just be 3 out front. A would be, let's think about this. So again, we're looking for how many groups of 5As can I take out of 10? Well, I could take out 2 groups of 5. So really, again, just 10 divided by 5. Same thing with the B's. How many groups of 5 can we take out of 15? 3 groups of 5. So 3A squared B cubed. Okay, and the next one, taking the cubic root of each. Taking the cubic root of 64, and I'm taking the cubic root of the expression that's to the 15th power. So cubic root 64, again, if we don't know that, we could type it in. So 3, shrink it down, 64, and that's going to be 4. Again, because 4 times 4 times 4, it's 64. So that's just going to be a 4 out front. And now the quantity, x minus 3, is now going to be raised to what exponent? So how many groups of 3 can I take out of 15 of them? 5. So 4 times the quantity x minus 3 is all being raised to the 5th. Okay, and just leave your answer like this too. You don't have to actually FOIL out x minus 3 5 times and then distribute 4. Don't do that. Just leave it like this. Take the cubic root of each individual term and then just leave it alone. Okay? The last one, so we're taking the square root of everything here. So square root of each term. So square root of negative 16, that'd be a 4i. That'd be an x squared, and y would be to the 4th. Okay, so there's your final answer. So on to the next page. So we got more of these groupings, basically. More of these binomials that are being raised to an exponent, but not too difficult. The first one, negative goes out front. The quantity is now going to be raised. So again, just keep the quantity all intact, but now just think about what the exponent's now going to be. So once we simplify it, the square root of that quantity to the 8th power is now going to be to the 4th power. Again, just leave it alone. Okay, don't do anything more. Just leave it just like that. For number 10, this would be negative. Keep the quantity all together, but now it would be to the 8th power once you take the square root. And the last one, final answer, would just be, I'm just going to go ahead and do this in my head. This would be negative 10. X is to the 8th, y is to the 10th, z would be to the 6th. And there's your final solution. All right? The next part, it says when you find an even root of an even power and the result is odd. Okay, let me break this down. So again, even root of an even power, but the result is odd. You must use the absolute value of the result to ensure that the answer is non-negative. Okay, so here's an example. It says if you take the square root, so square root again, that's even. So if I'm taking the even root of an even power, but my answer comes out odd. So if I take the square root of x to the 6, I get x cubed. Technically, you need the absolute value around it. Here is why. Okay, let me show you an example. What if x equals negative 2? Okay, there's my example. If x were to be negative 2, let's go ahead and plug in negative 2 and see how this kind of works. So if I plugged in negative 2 for x, I'm taking the square root of negative 2 to the 6th power, and we're saying that's equal to negative 2 cubed, right? So the square root, negative 2 to the 6th power, is positive 64. So negative 2 times itself 6 times, and this should be equal to the square root of 64, and then negative 2 cubed is technically negative 8. Okay? Again, when I'm asking you for the square root of 64, it should technically be positive 8 because I'm asking for the principal root. I just want the positive root, which is why you have to take the absolute value at the very end. So again, if it's an even index, an even root of an even exponent, and it comes out to be an odd, then you have to have the absolute value around your solution. Okay, so let me kind of show you what I mean. So for this one, for example, we got even, right? So I'm taking the 4th root of y to the 4th, but my answer is technically odd. It's y to the 1st power, so I need absolute value around it. Okay? The next one, we're taking the 6th root of 64. Sixth root of x to the 18th. Sixth root of y to the 12th. So taking the sixth root of each and every single term, the sixth root of 64, it's probably going to be 2, but if you don't know it, again, just type it in. Sixth root, 64, enter, comes out to be 2. Okay? Sixth root of x to the 18th, that'd be x cubed. Y would be squared, it looks like. Okay, but now double check and see, do I need absolute value around anything? Okay, I had even, that came out odd, so that needs absolute value. But y does not, because even, and it came out to be an even number, y squared. So absolute value only goes around the x cubed. Everything else stays exactly as you see it. All right. For the next one, square root. So we got square root 36, square root y to the 6. So square root 36 is 6. Y would be cubed. Again, technically even, square root. So even came out odd. Absolute value goes around y cubed. And for the last one, we're taking the fourth root of 16. Fourth root of x minus 3 to the 12th. So fourth root of 16, I already know that's 2. This quantity now, x minus 3 would be now raised, so 12 divided by 4 is 3, but again, even came out to be odd, so I need absolute value just around the quantity, just around the x minus 3 cubed. All right. Next part, what do we got here? Looks like we got a little story problem. So designers, it says, must create satellites that can resist damage from being struck by small particles of dust and rocks. A study showed the diameter in millimeters d of the hole created in solar cell by dust particle traveling with energy k in joules is about, and then they give us that equation. So it says to estimate the diameter of the hole created by a particle traveling with energy 3.5 joules. Okay, so basically we have to plug this in for something, 3.5 joules. Where we're going to plug it into? Well, it says K is in joules, right? So what we're going to do, this is K, 3.5. We're just going to plug it in for K, and we're solving for, it says to estimate the diameter. We're solving for D. All right, so we're just going to do an estimation here. So D is going to be equal to, we got 0.926, the cubic root of K, which is now 3.5, plus 0.169. And we could just type this all in. So again, we got 0.926, okay, times the cubic root. So if you want to put it in parentheses or put the times button, you can. Let's see, I'm going to do times 3. I'm going to shrink that down. We want the cubic root again of 3.5. Okay, now get out of the cubic root. So you got to arrow over once to the right. And then we're doing plus 0.169. So answer comes out to about this. So again, they just want an approximation. They want us to estimate it. So I'll just do to the nearest hundredth. We'll say it's about 1.57. And again, this is the diameter. And what are we measuring in? Diameter is in millimeters, it says right here. So it'll be millimeters. 1.57 millimeters. The next one says if a hole has diameter of 2.5 millimeters, estimate the energy with which the particle that made the hole was traveling. So this time we're estimating the energy. Okay, and we have the diameter. It tells us the diameter is 2.5. So we're doing this a little bit different. Now we're actually solving this for K. Okay, so here's how we do this. Estimate the energy. So let's see, diameter again is 2.5. So that's D. Plug that in. That's equal to, everything else stays the same then, so 0.926 with the rest of the formula. Again, we're solving for K plus 0.169. Okay, so start brainstorming, start thinking about how do you actually solve this? Okay, how do I get K by itself? First thing I would probably do, subtract. So we'll subtract this on both sides. Okay, so we're trying to, again, get K by itself. That's our objective right now. So let me do this. So we got, again, 2.5, and then we're minusing 0.169, and we get 2.331, which is equal to 0.926 cubic root of K. Okay, so again, we're still trying to isolate K. We want to get K by itself, but I would probably divide now by the 0.926. I feel like that's not going to be a really pretty number, so I'm going to take this result right here, that 2.331, divide that now by 0.926. And like I said, not going to be a pretty number. Okay, I'm going to write it down anyways, but keep it in your calculator. Don't clear out your calculator. Keep that number all intact. I'll just copy it down over here. So again, that's just 2.5172, 786. 1/8, and this is equal to the cubic root of k. Because I just want to explain this next part now. Thinking about how do I undo a cubic root? How do I actually get k by itself? Well, to undo a cubic root, what you're going to do to both sides of the equation to now solve for k is you're going to cube it. I have to cube both sides because again, whatever I do to one side of the equation, I have to do it to the other. So if you cube a cubic root, that'll cancel out the root altogether. You get k by itself like you want. So again, I'm going to take this answer in my calculator, what that current number, and I just want to cube it. So I'm just going to raise it to the third power, so answer cubed, basically, and it comes out to be this. Okay, so we'll again kind of estimate that. We'll just round it off to the nearest hundredth. I'm just going to say it's about 15.95 is K. And again, this is being measured in joules. So that'd be your label. And there you go. All right, guys, there you go. There's your next lesson of 6-4, simplifying radicals. So if you have any questions, let us know. Otherwise, have a great day.